So today let's take a look at my cat and also this interesting flashlight, which was donated to me. So thank you, and now let's take a look at it, let's test it, and let's take a look in it, of course. It's quite a nice flashlight. It's made of aluminum. It has a clicky switch here, the LED of course, and it's zoomable. It opens like this, and it takes standard lithium-ion cells, 18650 size. It takes 2 of them. Now let's test it. And it has a little problem with flat top batteries, because the flat top is not sticking out. Let's try another. And now it works. So it's high, medium, low, strobing, and SOS. It seems to work nicely. Let's try the zoom. It also works. And this flashlight has 2 lithium-ion batteries in a series, which means that this LED can have 2 chips in a series with just a resistor in a series for current limitation, or it can be a single chip in it and a buck regulator for current limitation. So let's find out, but before this, let's measure how much does it draw from the batteries. So those batteries are almost full. This is full. Also almost full. Let's put it in and measure the current using my clamp meter and this piece of wire, because it has a very low resistance, much lower resistance than any current meter. So let's set it to DC, zero it out, and measure the current. So it seems to draw about 0.73 amps at high, 0.39 amps at medium, and 0.22 amps at low. So the power input of it is the voltage times the current, and the voltage is 8.4 volts for 2 fully charged lithium-ion batteries in a series times the current, 0.73 amps. And this is about 6.13 watts. So it seems to be a 6 watt LED, or maybe 5 watts, and the rest of it is some losses in it. And now let's take a look in it. It opens like this. This is just a metal pipe. This is some holder. Here is the switch. And this is the top of it, with the most important part, the LED and some driver. It unscrews like this. And there is some lens, which seems to be plastic. And it's actually not removable from this. Is it glued in it or just pressed in? I can't remove it from it. And here is the LED with some heatsink. And this zoomable head. And a spring contact for the batteries. And this contact is also springy. And the next step to disassemble it is probably to unscrew this heatsink with some holes in it. So let's unscrew it using a wrong tool, like scissors, which fit into those holes, and it screws easily. And it comes out. And that's it. Now this one is completely empty. It's just a zoomable head, and so here you can see the LED chip in it. And here is the heatsink the board with the spring contact, and no components from this side. Can I pry it out using scissors? Yes. So this is the board with probably some buck regulator because there is some inductor, also some chip, some diode, which looks like a Schottky diode, and 2 transistors, or maybe some of them is a chip with 3 pins, some capacitors, resistors, and here's the LED. Can I take the LED out? It's now loose in it. And there is some ring or a reflector pressed into it made of a thin metal. Now it comes out. There is some plastic ring in it, which also comes out, and here is the LED. Now let's try to run it using a power supply. The voltage is about right, and it draws about 0.7 amps from the power supply. And at a lower voltage, 6.5 volts, it actually draws more. So even if the battery is almost flat, it still draws about 5.6 watts. So here you can see the current and the power at the different voltages, and as you can see, the power doesn't decline much. So there is a current regulation, and the current goes up at the input, and the current at the output is almost constant, and also the power. And as you can see, there is absolutely no battery protection. It will discharge your batteries down to about 2.7 or 2.6 volts, which is about 1.35 volts per cell. So it will operate the LED at a full power until the batteries are completely flat, which is nice, but it will happily keep discharging the batteries until the point where the batteries can be damaged or destroyed. Now let's measure the current and the voltage drop of the LED at 8.4 volts at the input. So the voltage drop of the LED is about 3.01 volts, and the current of the LED is 1.7 amps. So the power of the LED is 5.14 watts. And this is the input power. And the efficiency of the buck regulator is about 83.8%, which is actually not so bad. And here you can see the detail of the LED in it. It seems to be about 5 millimeters. And here you can see the board. Now let's try to draw a schematic of it. So here you can see the schematic of it, which is not so complex. It's basically just the battery, the switch, LED, and another 10 components. And I was originally thinking that this 3-pin package is a chip that does the 5 modes: the flashing, the SOS, and the pulse width modulation of the brightness. But it's not. This package is just a transistor, a P-channel MOSFET, which does the polarity protection. Of course, a polarity protection could be just a diode in series, but it has a voltage drop, so it's lossy. So instead of a diode in series, they use a MOSFET for polarity protection. And if the polarity is right, it turns on. If the polarity is wrong, it's off. And it's a P-channel MOSFET, which means that it turns on when the gate is negative in respect to the source. So when the battery is inserted right, the gate gets the negative polarity and the source of it gets the positive voltage via its body diode. But if the battery is the other way, it doesn't turn on because the gate is positive. And of course the transistor already has a diode in it, but it has a high voltage drop. A standard silicon diode has about 1 volt voltage drop, and a Schottky has still about half a volt at higher currents. But when this MOSFET turns on, it has a very low resistance. This one has only 47 milliohms or 0.047 ohms. And the current at most is about 1.7 amps here, and so the voltage drop on this transistor is going to be only 0.08 volts. So as you can see, this kind of polarity protection has a much lower voltage drop than a Schottky diode. And the rest of the circuitry is basically just a buck regulator, with an inductor, a Schottky diode, a transistor. This one is an N-channel MOSFET, so it's on when the gate is positive, and there is the current sensing resistor and the control chip, which controls the buck regulator, but it also controls the 5 modes. So it seems to be a 2-in-1 chip, which is probably specially designed for flashlights. And the chip basically measures the voltage drop on this current sensing resistor, and if the current is too low, the voltage drop is also too low, and the chip will increase the duty cycle to compensate for it. Like this, for example. And if the current is too high, the voltage drop is also too high on this resistor, and so the chip will reduce the duty cycle. Like this. The duty cycle is the percentage of time when this transistor is on. So the transistor is switching at a high frequency, and when it's on, the current goes from the battery through the LED, the inductor, this transistor, this current sensing resistor, and back into the battery. And of course the voltage drop of the LED is lower than the voltage of the battery. The battery is 2 lithium-ion batteries in series, which is about 7.4 volts in average, and the LED is just 3 volts voltage drop. So the rest of the voltage has to be dropped somewhere. If you drop it on a resistor, it will dissipate power and it will be inefficient. So now the voltage is dropped on this inductor, which gets about 4.4 volts in this polarity. So some of the power goes into the LED and the rest of it goes into the inductor, where it's being stored as a magnetic field instead of being dissipated. So the excess energy is stored in the inductor, and as the energy builds up in it, the current also goes up, and at some point this transistor turns off. And now the current from the inductor goes through the LED and this Schottky diode in a circle, basically. So now it's not using the energy from the battery, it's recycling the energy from the inductor, so it's quite efficient. And at this moment, the polarity of the inductor is the other way. It basically supplies a voltage for the LED and this transistor is off. And the current goes down as the energy runs out from the inductor, and at some point this transistor turns back on and it all repeats. And there is also some filter capacitor in parallel to the power, and there is a filter with a resistor and capacitor to reduce the voltage ripple that goes into the chip. And there is also some omitted capacitor on the board. I'm not sure what it was. And the chip has the output for the gate of the transistor and the current sensing pin. And now let's try to see it on my oscilloscope. And of course I will have to put the LED on a heat sink so it doesn't overheat during the measurement. So now it's all connected. So the ground of the oscilloscope goes here. One channel goes here to the gate of the transistor, and the other channel goes here to the drain of it. So here you can see the waveforms on my oscilloscope. Here is the gate driving waveform, and here is the output waveform on the drain of the transistor. So as you can see, when there is a positive voltage on the gate of the transistor is on and it pulls the voltage down at the output. And when there is a zero voltage on the gate of the transistor is off and the output voltage is high. And when the transistor turns off, there is an overshoot here. And at the medium power, the switching only happens for about 50% of time. So as you can see, here it's switching from here to here, and here it's not switching from here to here. And at the low power, it's switching for about 25 or 30% of time. It's switching here, and it's not switching here. So the buck regulator is switching at about 540 kHz, and the medium and the low power is done by interrupting the operation of it at about 270 Hz. Which means that at medium power, the buck regulator makes about 1000 pulses and then another 1000 pulses are omitted. So this is actually 1000 pulses and you can't see the individual pulses on the oscilloscope at this scale or at this time base. What you can actually see on the oscilloscope is this. So this kind of waveform shows up as one solid line and one interrupted line above it. And 270 Hz is quite a low frequency, which can cause some interference with cameras, some flicker or bars. But it's not visible to human eye. Now let's try to put it back together, and I have to say that this LED doesn't have much thermal contact with the heatsink. It's basically touching it just by this edge, not by this surface, which had no heatsink compound before I added some for my temporary heatsink. So as you can see, just a very narrow edge of the LED is sitting on this ledge, which is quite thin. There is really not much surface in contact with the heatsink. So this is the LED touching the heatsink just by a small area here and here. Why this is not bigger like this? I can't really do much about it, it's not really designed well. So let's put a bucket of thermal compound on it. So this is a Chinese thermal grease. A nice bucket, but of course it's half empty. Even a bucket of it can't really save a poor design, but let's try it. This is just a horrible mess. It will probably end up on the chip anyway. Let's put this cover on it, which will probably force it onto the chip. Miraculously it didn't. Now let's cover it like this. So that's it. A horrible mess, of course, and I pressed the board back in and now let's test it. It seems to work. So this flashlight is not so bad, but the heat sinking is a bit questionable and it also discharges the batteries very deep, so you have to use protected cells, or alternatively you could use just one cell because it can run at quite a low voltage, and if you use just one cell it doesn't have to be protected. It will discharge it to about 2.7 volts instead of 1.35 volts per cell. And this flashlight comes from eBay for about $3.89, including shipping, and it was donated to me by a viewer, so thank you, and here you can see the keywords. And of course this is just completely ridiculous. 90,000 lumens. The best LEDs have the efficiency of about 150 lumens per watt, so for 90,000 lumens you need about 600 watt LED. So they apparently put at least 2 extra zeros in it. So this is Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And I also plan to test more cheap lithium-ion cells and also to take a look at some pressure meters or pressure gauges like those.